Last time we stopped at the section that was dealing with simplifying various expressions in order to get identities justified. And that was a section that skills from which we're gonna utilize in the following sections as well. So it's gonna be with us. Of course, problems that will be with us are a little bit more reasonable than the ones that go farther into this section. So I guess we'll just do an exercise and move on. So I'll try one, let's say 27 is recommended. And I also want to say that I'm still waiting for your work. If you did not submit your homework for the midterm yet, I still have some people that working on it, I hope. Also, if you still even owe me midterm or want to redo it, I told to the class that I will accept for a little extra that, and usually that helps to get a better grade. I never mind to spend a little extra time grading, and people send me their work a little by little. So if you have something to send to me, well, then just don't hesitate, send it to me. Grades are on the Canvas, so you can always check it. If something is unclear, I'll clarify, just let me know. And here's the question. Identify, or actually prove the identity that product of two parentheses is actually tangent squared. Well, I guess this be something that called standard, because we can recall such a formula that a minus b multiplied by a plus b is the same as a squared subtract b squared. So with this formula in mind, I will notice that instead of a, I can use secant, and instead of b, I get 1. So it's going to be secant, trying to write secant here, squared theta subtract 1 squared. So this is my so-called left side. So this left side is what I'm going to be working on in order to produce my right side. It looks like when I subtract secant and 1, we can utilize the formula that is called sometimes Pythagorean identity, that 1 plus tangent squared is a secant squared. I hope you're familiar already with this formula. It should be here among the standard trig identities. That's called Pythagorean identities. It's in the beginning of section. Or all of these formulas are also placed at the very end of the textbook. So the one that I'm talking about is here. 1 plus tangent squared, or tangent squared plus 1 is a secant squared. And therefore, if I bring 1 over to the other side, in other words, people say subtract that number 1 on both sides of this identity, then you're going to have just a tangent squared, which is same as a secant squared subtract 1, tangent squared of theta. And this is exactly what I needed to prove. So that's my right side. So just a couple of steps and we're done. So I think this level of identities is something standard. Of course, if you keep trying more and more, well, that's a beyond standard level. And if you plan to go for a calculus class, then you should, I guess, redo all problems I've done in this section last time, and I'm gonna do it now, and I will update what's on Zoom. I'm talking what's on that YouTube channel, because problems of this kind you will never see, I guess, unless you take differential equations class and so forth. So I would say this page is already questionable, even if you go for a calculus. But if you feel comfortable with those problems, and if you don't go for calculus, well, maybe you should, because this level of exercise is called standard. And that's good to realize, I think. So we're going to continue with some more, as usual. And we're going to actually look at the next group of exercises, next section, that actually is dealing with more and more involved formulas. Again, all of these formulas are on the back of the textbook, so you can easily locate them there. And they actually have a justification for this, but so you can see cosine of sum of two angles, alpha plus beta. But to read this justification takes time, and if you wish, you can read them. So we get a cosine minus sine. That's how I remember it. Minus sine times sine alpha, sine beta. So that's what this actually says. Cosine alpha, cosine beta, sine alpha, sine beta. Down below, there is another formula, which is pretty much same, but it changes. Plus with a minus and vice versa, minus with a plus. And that's why sometimes people write both formulas this way. So they say, if you have with a minus sign, then the lower one, which is plus, will appear. So that's a short way to describe both of these formulas. And here's the justification. So they started with geometric structure, and then they used the distance formula in order to prove it. They used it a couple of times. So it is just a tedious process. But again, if one is interested, then you can definitely try to go over this. And then there are two identities that appear right out of this story. So for the cosine of, so let me try to utilize the formula here to see what will be cosine of pi over 2 minus theta. Minus theta. So all I have to do is utilize the above formula. Try to write cosine a little bit nicer. See, after this update, something happened, and I had another update, and it's really, when I start erasing, it erases way more than I am trying to. So it's very helpful, of course, but not really, right? So anyways, this is going to be according to formula above, cosine. So cosine of first times cosine of second, which is theta. So that's the use of these formulas. So now, since it's a minus, I go now with a lower sign, which is a plus, and that'd be sine first, which is sine of pi over 2, and the second is going to be sine of theta. Well, now it's time to get my favorite unit circle, to get to see what's with pi over 2, and that's the point on the unit circle, right? Coordinates are 0 and 1. And first coordinate is always cosine of this angle, and second is always sine. This is a unit circle story that appears again at the end of this textbook. Remember that big diagram, I just produced a piece of it that I need. And I just noticed that 0 will stand instead of cosine, and number 1 will stay instead of sine. And that's why this piece will disappear, right? And all we're left with will be just 1 times sine of theta. And that's exactly what they have here. That's interesting, right? So formula way to show this result. And that actually checks that formula is working. Well, how about if we take a look at the friend formula, or people say sister formula of this? That's a formula for a sine of alpha plus beta. they say sine of sum. Turns out this is going to be sine cosine plus sine cosine. So sine alpha cosine beta. So we say sine cosine, it means that's first angle, second angle. And again, sine cosine, and that'd be now not the same, but the second angle times first angle. So I memorized that formula, and analogously to the one above, if you happen to have a minus, then sign changes here with a minus. And this will help me to justify the second identity here that deals with, again, angles pi over 2 and theta. So we're going to have sine cosine, so it's a sine pi over 2 cosine theta. So it looks like that's a little exercise analogous to what we can see in the textbook all the time. So now sine theta cosine pi over 2, right? And again, I'm going to use what we have here on the bottom. So instead of cosine, I put 0 pi over 2. Instead of sine, I put 1. So it looks like now this piece disappears, and 1 times cosine will be same as a cosine of theta. And you see that's exactly what the formula established. So we have that use of formulas, and I think that's pretty neat because these two formulas actually help us show that if we have pi over 2 minus angle, then cosine changes with sine and vice versa. And sometimes people call them as co-functions. So they kind of change. Same co-functions are tangents and cotangents, or secant and cosecant. So what else is here? Well, there's some, oh, here's the formulas for sine. So it looks like they should have utilized them, but somehow they put those identity prior. There's also a formula for tangents. I guess it might be a little bit too much to put on so many formulas on you. I think we can just practice to use the ones that I have listed here. So let me take a look at exercise, let's say number 11. So they say find exact value. Remember, exact value is when you don't use calculator. We can put it in the calculator and it's going to give you approximate value, but what they want is exact value. So instead of 5 pi over 12, they want to write sum of two angles. So what angles that are familiar to us could produce pi over 12? Well, it turns out that's probably pi over 2, pi over 3, pi over 4, and so forth. So if I try, for example, pi over 4 and pi over 6, for example, then my common denominator will be 12. So there'll be some 12s. And so this exercise just wants you to decide how can I produce this 5 pi over 12. So if this is 6, I can multiply by 2 to get 12, so top and the bottom. And with 4, I have to multiply by 3, right? So we end up adding 3 pi and 2 pi. Yes, that's exactly 5 pi over 2. If that didn't work, I would have tried not pi over 6, but pi over 3, for example. So I guess that's the place, which is something that is a little different. So it requires you to, I guess, practice deciding how to split your angle into two. So now what I'm going to use is a formula that we just saw for sine of a sum of two angles, because each of those pieces I should be able to take. So what I'm using is this green formula. So this will be sine cosine, which means it's a sine pi over 4 cosine of pi over 6, plus, again, sine cosine, but now they switch pi over 6 with a sine and pi over 4 with cosine. And again, we need to get the angles actually worked out from our favorite little unit circle. So let's recall pi over 4 or 45 degrees. Remember that sine and cosine are both the same, right? It's like a square root 2 over 2. You can again check with the end of the textbook. So square root 2 over 2 will work for both. And this is going to be my entry here and entry there. Okay, so I go ahead and replace with square root 2 over 2. And this one and that one to start. And now I get angle pi over 6. Maybe I get a separate picture here. It's a little bit bigger. I can better see it. So pi over 6, that's pi over 3 here. So one of the coordinates is a half, and looks like a half is here with angle pi over 6, right? Here is a sine, y coordinate, and this is a half, right? And the other one will be cosine, and that'd be a friend of 1/2 is root of 3 over 2, right? So that's a cosine pi over 6. And this is great. So we got those two to replace. So instead of cosine, I put root of 3 over 2. And instead of sine, I put a half. Okay, great. So let us add these. Notice these fractions have denominators 4 for both. So first is root of 3 times root of 2 is 3 times 2, 6, plus 1 radical 2. Just like that. That's definitely not approximation. This is exact value. So that's a usage of this formulas. One can say, Alex, I could just put this in the calculator and that's it, because what kind of fraction is root of 6, root of 2? And I would say, yes, I agree, but these formulas are good to get used to, because if you get used to these formulas, the next section will heavily utilize them. But indeed, those formulas by themselves probably are not as very useful, but the stuff that follows is important. But today we'll just practice a little bit using these formulas. That's all we need. So how about the next group of problems? If we tried, say, exercise number 25, that's a recommended exercise, looks like. So let's try, see what happens there. Well, what happens is we have cosine, cosine minus sine, sine. So I recognize my very first formula. So this is going to be a cosine of, since it's a minus, if it's a minus sine, sine, then it's actually cosine of sum. So you have to add 70 and 20. So it looks like that one works right away, if you are familiar with the formula. If you're not familiar, well, then who knows what this is, right? So this is actually cosine of 90 degrees, and we just saw what cosine of 90 degrees was. 0, right? So cosine of 90 is 0. That's what it is. Or you can check it with a calculator if you want. But make sure you put in degree mode, because if you put cosine of 90 without degrees, it'd be radians, it'd be something totally different. Remember, whenever you use calculator, you should be careful. You should make sure that mode is right. Well, we do another one in the next group of problems. And then we'll say a few words about tangent, maybe, and that'd be good enough. So how about if I try problem number like 33, another problem that we could consider. Problem 33 has 4 parts, A, B, C, D, and that's it. So let's try part A. That's dealing with a sine of alpha given to us. It is 3/5. And then I also have a cosine of beta given to us. It is 2 square root 5/5, whatever. So in the first part, they want to sine alpha plus beta. And this is going to be exactly my formula that I wrote above in green, so I can copy it again. Sine alpha cosine beta, right? And then plus, the sign goes same, so that's sine beta cosine alpha. Okay, so I'm going to be using this, but there are a few ingredients missing here. So for sine, I need cosine. So remember that. Let me write that favorite Pythagorean identity somewhere here. Sine squared plus cosine squared for any angle is equal to 1. So you get alpha or beta or theta, whatever, as long as it's the same angle. So I can actually pull out cosine of whatever alpha. It's going to be a square root from 1 minus sine squared. But we need to be careful because it could be either positive or negative. It depends where your angle is located. What I mean is when you have given that sine alpha is 3/5, which is someplace here, sine is always on the y-axis, then there are two corresponding points on a unit circle. So that's the important part here. So there are two possibilities. So one could be positive value, and the other could be the same but negative. How can I decide? And the answer is they give you quadrant. They tell you that you're here in the first quadrant because you're actually dealing with 0 to pi/2, so it is going to be positive. And that's why we know uniquely what happens, so we don't take that. If they said it's in the second quadrant, I would have put a minus. And that's important to realize. So anyways, I'm gonna replace now with 3/5 that, so I'm gonna go with the square root, it's positive, 1 minus 3/5 squared, and do some arithmetic here. So how can I do this? Well, I guess I probably should continue on the other side because not enough room. So we're gonna have a 1 minus 9/5 squared, 9/25. So I can write instead of 1/25/25. So when I subtract 9/25, we're going to get a 16. So the square root will be extracted from 16/25. And this is 4/5. And that's our cosine. 4/5. So I know what to put instead of cosine of alpha, which is here, 4/5. And by the way, I can right away also put 3/5 instead of sine alpha, 3/5. Good start. Now we go with beta. So they already gave you that cosine of beta is something like that. So I'm going to put that fraction 2 radical 5/5. Okay. So they multiplied. So the question is, what's sine beta? Well, analogous formula will be utilized, but let me get room from this. But that analogous formula is now isolating my sine function. And of course, I also have to decide, is that going to be a positive or negative in front? So let's pull out function sine. So it is going to be subtracting that cosine from number one, that cosine squared, and extracting square root, and of course deciding, is that going to be again positive or negative? See, in the formulas they put plus minus, but that's not negative. Correct way to think about this, because it's either or, it's never both. That's important to realize. Okay, so let me get the sign of that, just like we did in the previous example. I'm going to think about the what? Quadrant, right? So if they told me it's 2 radical 5 over 5 for the cosine, I think it may be a little bit too messy. Maybe I'll put it here. Cosine is something positive, right? 2 radical 5 over 5. So all we know is that cosine is on x-axis and sine is on y-axis. So once I have that on my picture, I can see 2 points on a unit circle that correspond to this x coordinates. So there are 2 angles. So the question is, which one should I take? And the one I should take will be in the quadrant number 4, because there we have negative pi over 2. So this is going to be here. What does that mean? Well, it means that our sign is also negative. So it is not positive, it is negative. Let's plug the numbers in. So I already know it's negative, so it's going to be minus. And now I have to subtract the square of this 2 radicals 5 over 5. Okay. 2 radical 5 over 5. This is going to be squared. And we're going to have to simplify this. So we get a 1, or actually 5 squared will be 25 over 25. I'd rather write number 1 is same thing divided by the same thing, right? Subtract 4 times 5, which is 20 over 25. So from 25, I will subtract 20, I get 5 over 25. Or I could also treat it as a root of 5 over 5. This is my, again, sine alpha. Sine alpha, we also find that. So it goes here, root of 5 over 5. This is lengthy exercise, right? Lengthy. Well, for a change, you can try one lengthy. So I found that 25 was my denominator, 5 times 5. What's numerator? 3 times 2 is 6, root of 5 plus 4. Root of 5 is going to be 6 and 4, 10 roots of 5. And some people can say you can divide by 5, so it'll be 2 root of 5 over 5. Okay, that's the answer. Again, exact value because it has a square root 5. And that's pretty much all this section is actually talking about. They want you to get used to these 2 formulas. And maybe, I don't think I want to give you a quiz. I know it's been a break, so you're probably still not getting on track. Plus, well, these sections, they have pretty tedious exercises, so maybe later. I'll try to just show you the formula for tangents, just to write it down. So that's tangent of alpha plus beta, tangent of sum, people say, is the following. Tangent alpha plus tangent beta, the sum of them. So I'll do one exercise using this formula. And denominator is 1 minus tangent alpha times tangent beta. Turns out you could actually justify this formula if you divide sine by cosine, and then you will have fractions to mess with a little bit if you interested, you can try, or you can just read how it's done above in the beginning of this section. So let me try to utilize this in order to do part D of this exercise. How about that? So in part D, they actually call in for tangent alpha minus beta. And analogously to the formulas that we already saw here in this section, if you change plus with a minus, the plus changes with a minus in the formula, so it'll be minus tangent beta. And minus vice versa changes with a plus, so it'll be 1 plus tangent alpha times tangent beta. So how can I find those? Well, I already have everything I need, because tangent alpha is a sine over cosine, right? Same with tangent beta, sine over cosine. So alpha. So sine, we already saw what it was. 3/5, right? Over cosine, over sine. So sine over cosine. What did I write? I think I just need to be a little more careful. So you start to erase, and it erases a little bit more. Nice. Good update. Cosine. Sine over cosine, right? That's tangent. So we got 3/5 for sine, and what's for cosine? Well, that was given to us 2 roots of 5 over 5. Okay, whatever it is, you divide. Now this 4-level fraction is something we definitely don't want to deal with because of this denominator and this denominator. They're both 5s, so multiply by 5 here and multiply by 5 here. So this way the denominators disappear, right? And what's left will be 3 only on the top and 2 roots of 5 on the bottom. So this is my tangent alpha. Same way I'll find tangent beta. So again, I divide sine by cosine, sine beta by cosine beta. And then we're going to get the fraction. So sine alpha. Did I do it right? I think I should be careful because I think I wrote cosine beta and sine alpha, and that was bad idea. I think this is not right, isn't it? Because I wasn't careful, because I didn't pay attention to angle, because sine alpha is here, right? Sine alpha. Now I need cosine alpha. I need 4/5. I think I should erase that. I think I better erase that because it's just not right, because I wasn't careful. But I think it's good that I wasn't careful, because it's showing you it's not a big deal. You can always fix your mistake quite easily. So you get a 4/5 for your denominator. You do exact same thing, times 5 here, times 5 down here. 5s cancel, right? So it's the same process, just a little different number, right? Wasn't careful. I put wrong fraction for cosine. So now I will be careful. Now I'll put right fraction for the cosine. So with beta, my sine of beta was found here. We struggled with it for a while. It was right there. The root of 5 over 5, right? And that will be my numerator. Okay. And denominator will be that 2 roots of 5 over 5. Okay. Oh. See, it is very tedious. These exercises, you definitely want to get a bigger piece of paper to do, because saving room always brings to the mistake. And I hope I nicely illustrated it for you. So get more paper, that's the message. So what cancels here? We have a root of 5 and we have 2 roots of 5 in denominator. Notice the root of 5 also is going to cancel, so it'll be 1/2. How about that? Okay, so now it's time to use this formula. So I'm going to plug into this formula the tangents. So one will be 1/2 and the other will be 3/4. So they're not bad, right? So tangent of the alpha is 3/4 minus tangent of the beta is 1/2. Okay. Now 1 plus, now we also have product of these two guys, 3/4 times 1/2. So what bothers me here? Of course, denominators, right? Too many denominators. And I'll show you how to clear them all at once. So common is 8. So I multiply by 8, top and the bottom. But I must distribute this 8. I must multiply each term of this fraction by 8, because then these are all going to cancel, these denominators that bother me. So all I'm left with on the top will be 2 times 3, 6, minus 1 times 4, 4. You see how nice it is right away? So you don't have to worry about this common denominators. I know some people say, oh, I'm going to common denominator everything. Don't do that. Get rid of them right away. Plus 3. So here's my answer. 2 11ths right away. So I guess the techniques of working with this so-called complex fractions by multiplying and the top and the bottom by the same exact number, so your denominators will go, is pretty standard. It saves time, and it gives you less chance to make a mistake. You do it right. That's why I highly recommend you to redo this exact same part D with these fractions, and I think that'd be helpful, because you do it once, then you know how to do all of the problems. In fact, remember, I always recommend to do a couple of problems per lecture. So I think if you do this, one with tangent, one with either sine or cosine, that's it. That's all you need here. So as promised, I'm not going to give you a quiz today. It's just too much. These problems are very involved. In fact, the rest of this section, this chapter is involved with lengthy exercises in the next section and the one after next. So I don't think I'll be giving the quizzes on this chapter, but I'll just ask you to try to redo exactly the same problems that we've done in class, especially part D. I think if you know, if you can follow with part D, then you're good, right? And that's actually how you learn math, because you just take a piece of paper and you do exactly the same exercise. And then after you've done some steps, you check and see, is that you following the pattern? Did you make a mistake? And I guess that's the way to actually learn it. It's not just taking some brand new exercise and start doing it and getting stuck. You get stuck, you see how I worked it out by checking that recording, and that's the way to go. And then you do another one, and after that, I'm sure you can do more if you need, but I think that should be enough. Couple of problems is good. So I guess that's pretty much all in here. And I'm gonna, next section now deals with double and half formulas. So next section I'm probably gonna do in 2 class meetings, because double angles and half angles would be way too much. So anyways, I'm gonna stop here. Oh, I wanted to ask you, that's they emailed me this whatever class climate when you do the student evaluations, and they said like only 3 people in class did evaluation, so they wanted more. So if you don't mind, if you can please go to your old email, you probably get it like a couple of weeks ago from those class climate. I'm not sure, because I never get those emails. And just fill these evaluations for the class. That'd be very nice because they want to see a little bit more response than just 3 people. That's really not many. Okay, so I'm going to stop at this stage, no quiz, so just let you go. And again, weekend is coming. How about that? So enjoy.